Starting with the next talk. So for the next talk, we have Spaarsh Thakkar from IIIT Surat in Gujarat, and he does Debian packaging. He's a Debian candidate with GSOC for GSOC 2025, and his talk is about a very unique problem, which is problems in packaging. So every time you install a package, everything goes smoothly and it works, but there's a lot that it takes to make that happen. So the talk is Packaging Pain, the GPU Developer Edition. And Spaarsh, the stage is all yours.
Yeah. Can you set up your presentation?
Disconnect it. The cable is here.
Oh, thank you. Okay, so I guess the mic is working. Yes, I suppose when the Thanos guy decided to ditch his session, I guess he snapped half of my audience out of the hall. But nonetheless, so let's start with the session. Who am I? So I think Ashutosh gave a apt description. I'm a final year undergrad student at IIIT Surat. I'm a GSOC 25 contributor with the Debian organization under the mentorship of Corey Bloor. Most probably he won't be watching this, but still a shout out to him. And yeah, I'm a Debian package developer with the ROCm team. So essentially what we are trying to do is how to get AMD's ROCm stack into existing Debian packages and get new packages out there that help the community and the users that are trying to use the ROCm stack. ROCm is something that AMD has came up with. It's like AMD's CUDA stack. So that's about that. And my work, by and large, it's just a formality. I'll skim over this. I published a package called HipBlast Common to Debian Unstable. I'm working on enabling ROCm in various Debian packages. Some of the packages in progress are DBCSR and Glue. They caused me a lot of pain. Some planned work is enabling ROCm in CP2K and working on HipBlast LT. So now, why do you care about Debian packages or packages in fact? So whenever you run apt install xyz, you are installing a Debian package which has been maintained, tested and distributed by a lot of Debian volunteers. And even outside of the Debian packaging ecosystem, packaging software in general just helps you when you have a lot of software flying around in your systems and you don't want people to just pull in something random from somewhere. Maybe the latest commit broke something and you don't want to have a direct link to whatever latest thing you changed. So you package software and then you distribute it. So now essentially it's under your control what version of software is being used by the people. So that's why you should care. Now, what is a package? So mixture of executables, libraries, headers, dependencies, along with installation instructions. This is maybe something more specific to Debian, I guess. And all of this is packed into a single binary. So that's a package. So to put it very simply, you have source code and you have build files, and that by and large makes a package. It's a very vague definition, but it almost works. Now, what's a build file? So story time. Once upon a time, there was a developer who wrote some C code, compiled it, got some executable, ran it, got an output. Fantastic. He wrote more code, and then he was like, okay, I'll have to split my code. He compiled one file, then he linked it with another file, he compiled that, and then he got the executable, and then he got the output. And then he wrote some more code, and then he split things even more. There was more compiling, more linking, and as you can see, things got out of hand pretty quickly. And as you factor in headers, this was a very simple example, linking. But as you factor in more stuff, there will be shared libraries, there will be static libraries, there will be header files, there will be dependencies, whatnot. So more and more steps get added, and one of them is crying. So that's why we came up with CMake or Makefile. Makefiles came first, then came CMake. And we refer to these as build systems. So that is what I mean when I say a build file. So to put it very simply, a build file is the place where you write what thing goes where, what components are linked together, what overall will eventually lead to the building of the final package that you have. It can be a shared library, static library, maybe some very simple files that won't even be executed. Now Debian packages even have these documentation files. So that's what a build file is about. So when I say, so all of this graph stuff, it is like abstracted by your build configuration, and that is what the build file has. So that's about it about packaging in general. But what's different about Debian packaging? So the Debian folks came up with, so what they did was they took existing packages and then they just added one additional component to it, which is the entire Debian directory. So the Debian directory is sort of like, it is isolated from the rest of the package. The source code, all of this, these two are maintained by different versioning systems. So as long as you are changing something in the Debian files, Debian will be all right with it. You mention it in the changelog, and that's about it. But as soon as you change something in the source code or something that is outside of the Debian directory, Debian is like, please make a note of that and make a patch for it. That's what patches for packages do. They make some change to the source code or to the build configuration, something outside the Debian directory. So I'll just go over some very important files that around which an entire Debian package developer's life revolves around. So one is rules. So as the name suggests, rules. How do I build this? What parameters will I pass? Compiler flags essentially, and what build file to use. So someone is using makefile, maybe this one is using cmake. So what all goes into what all rules are to be followed when someone will be building this package. That is what the Debian rules has. Debian control is what will be the package name, what will be the binaries involved in this particular package. Libraries included, dependencies, build dependencies, runtime dependencies, and a lot of metadata. It's for a large part, it's also upstream metadata. So, and the third thing would be the Debian changelog. So what changes were made which led to this new version, and now you're publishing it to which particular branch. And the other thing that I mentioned, a fourth good honorable mention would be the patch system. So Debian has another directory patch, and in patches you have, these are essentially Git files, to be honest. So whenever Debian so what Debian does is that when you give the packaging system a tarball, it will take the tarball and then it will go over the patches that are supposed to be implemented on this. So these are Git files, so it will manually unpack the tarball, it will go to the files that are supposed to be changed, and it will rebuild the packages code and all of the stuff until the last patch. And then it starts the actual build process. So this is a very good way of isolating the work that a package developer is doing simply to publish something out there. And then there are some changes that are more of changing what the source code was doing, or maybe naming like changing a few stuff here and there. So that was about the background of what Debian packaging is about. Originally, I was only going to go over the background, but then I decided to just screw it and go over more complicated stuff, because I guess you can handle it easily. It's very interesting stuff, to be honest. It would be a shame if I don't mention this. So quick primer before I get into the whole GPU packaging thing. So for maybe you need a brush up, maybe you know this, but I'll just mention this anyway. So kernel is a function that runs on a CPU, on a GPU. Very simple. It needs two things: the code itself, what am I supposed to compute, mat, mul, whatever. And the second thing is the launch configuration. So how many blocks should I allocate to this, so on and so forth. So these two things by and large make a kernel, and you have this code, you compile it on a device that has a CPU, and then you send it over to the GPU just to execute it, and then you finally get the output and stuff. So these configurations affect performance, and hence they must be tuned on a per GPU architecture basis. Now, the other thing, parameters. So each kernel, like the function that will run on the GPU, is launched with these specific thread block configurations: number of threads per block, number of blocks, shared memory size, and this and a lot of other stuff. All of these are referred to, or at least I will refer to for the rest of the talk, as kernel launch parameters. So, and these values, as I gave a very brief information about them, these values depend very heavily on the GPU architecture for an optimal performance. What works for one architecture just won't work for the others, because the memory size is different. You have more number of cores in that GPU. It's just too varying to be able to come up with something standard or something. So that was a quick primer. Now I will get into the actual thing. So there was a package, there was a problem, and then there was me. So GPU code is not portable. As I said, we take this for granted. We never even have to think about the architecture that my CPU is going to use, because all of the CPUs are using x86 as far as we care. So that standardization does not exist for GPUs yet. maybe that will not change for quite a while now. So even so, of course, different vendors will of course have different architectures. But even for the same vendors, they have several series. They will release a new series that will have a different architecture. So the point is that the code that you wrote for one particular series or for one particular vendor just won't work when something new is released, some new architecture comes into picture. And by saying that it does not work, I'm not saying that it will run into some runtime compilation. That can also happen, but it will just be unoptimal, and you don't want that because GPU takes a lot of power. And other than that, the lack of portability. Since I'm discussing AMD ROCm, I'm just talking about architectures, but AMD has its own ROCm stack, the whole HIP stack, and NVIDIA has CUDA. Then you have OpenCL. So the code, the entire stacks are varying. Even there, the architectures are varying. So what kernel parameters to go for, no one knows. We just keep figuring out as we keep going. So the point is, GPU code is not portable, and I learned it the hard way. So what this means is that it is difficult to build a one-fits-all binary. And this is the part where my work as a Debian package developer becomes a huge, this is why this is a very big pain point for me. So because now I have to build multiple binaries for n number of architectures. I was fortunate enough that the packages that I'm working on support 3 or 5 architectures, but I know of one of my fellow contributors that library was supporting 20 architectures. I can't run the compilation 20 times and still have a life. So we need to find some way to do this. And because understand this, when you pull in packages from the Debian APT repository, it's not that Debian compiled it or something. I, as a package developer, I compile it and then I submit it to Debian mentors. Someone approves it, tests it, and then it is simply pushed. So the compilation power is mine. It may be tested by other people, but it is me who is doing the compilation process. And I then simply submit it. So that's one thing. So I have to build multiple binaries to support multiple architectures. Or I just use a fat binary. So a fat binary is a concept that NVIDIA CUDA introduced. So to put it very simply, it's like one binary that can support multiple architectures. So of course, as the name suggests, whenever you go for something so generic, you get this performance trade-offs. Again, we don't think about this a lot for CPU because of course there is no generic thing for CPU. There's only one architecture. But for GPUs which are anyway so power hungry, these fat binaries are not a very preferable way to go by. But as a package developer, I would like if some package only has a fat binary because that makes my life easier. But so that's by and large the point. It is very difficult to build a one-fits-all binary. So now the problem. This is not the problem, interestingly. The problem is that GPU-enabled packages often do not support generic builds. So despite this not being too common, it's not like that the NVIDIA build configuration does not support multiple architectures, or the ROCm build configurations do not support multiple architectures. I can pass the architecture simply while compilation, and one binary will support all of the architectures that I mentioned. Same goes for CUDA, which actually coined the word fat binaries. But the problem is that since this is so unoptimal, package like the source code developers just don't go for it because it's just so bad. And so they just support one architecture at a time. This becomes a very big problem for me because now all of a sudden a simple dependency graph that was supposed to be this is like each node has like 5 or 6 subnodes, and I have to figure out how to connect what with the thing that is dependent on this thing, and it just becomes very complicated very fast. So as I said, the challenge is package may not support fat binaries, and there are even some packages that have their own custom build flags. So this is like a big nightmare because now I have to go through their build configuration. I need to understand why this custom flag exists, what it is trying to do. At times I'll have to go upstream, I'll have to see that why was this thing particularly implemented, because I need to understand that, because that is what my Debian rules file is going to do. I will pass the flags and then it builds the file. I have to decide what flags are supposed to be passed. So these are a bunch of problems that you come across. Now the package. So this package, it just won't allow me to build a fat binary. I tried fat binary flags. It just won't build. I went into the build configurations. Turns out it just went, if someone has turned on this flag, turn it off. I was like, wow, they really don't want me to have a fat binary. But they had a reason for this. I mean, I may make fun of that, but they had a very nuanced reason. When I went to the upstream code, which no package developer wants to go for, but you have to, because your job is to ensure that their code is distributed well. So it's not that we are nemesis of each other. It's just that we have quite different priorities. I want something generic. They want something that is the best for the user. Both are fighting for the user, and this is worth a fight. So when I went into their the entire build process, I came across the parameters. So the parameters come into the picture now. So when I was building the process, I saw these few things being logged in the output. And as you can see, GPU version MI250. It's an AMD GPU. About to process 432 kernels from file parameters, something a JSON file. It has a WOP size decided. It will take these parameters from the JSON file. It will put it into another file, and eventually all of this is copied into the parameters.h, which is finally used to build the final package. As you can see, this is problematic because, first of all of this is happening outside the build process. So these are Python scripts that are guiding this. So there is no way that I get to manipulate this without getting into their package and changing stuff. So this may mean a patch or an upstream change that I have to negotiate with them. So this was a problem. And as I said, 432 kernels tuned specifically for MI250. They did this for a reason, because they had ran experiments and they came to realize that these are the optimal set of values that you should use if you want to run this at the maximum efficiency. And then eventually these are compiled into parameters.sh. And that's why they had a very architecture specific build. So I mentioned the hardware that they were targeting, but of course they go by the hardware, and then they have a map that for this hardware go for GFX so and so. So essentially they are going for an architecture specific build, and hence it was by design incompatible for generic builds, at least the ROCm backend. They had a generic build for OpenCL, but the point is that even though OpenCL has worked out pretty good so far, the problem is that now when AMD has specifically made ROCm to run well on AMD hardware, it should ideally, I can't say for that, and slowly, hopefully, gradually, ROCm generic builds will outperform OpenCL. It still maybe 1 or so years far away, but we are already seeing some improvement somewhere. But the point is that this particular package by design was just not allowing me to make a generic build. And now, why all of this is happening? Why even did they go to so much troubles? They found out the optimal values for 432 kernels. There was a reason for that. And it is the optimization problem. So the optimization norm, So even, and this is not only something that this package was doing, even for high performance BLAST libraries, I have seen that they manually choose which kernel to go for, essentially which kernel parameters to go for. And based on that, they are like, yeah, just go for this. And they just run it. So all of this was happening internally. So they tune for a specific architecture. And based on this, they select different launch configurations or optimized kernels, depending on the GPU that you're targeting. So this is not something new. It's something very standard. It is standard to a fault. No one even takes this. No one even. When I first came across this, that wait a minute. So all of this is like bunch of if-else statements. It was a bunch of if-else statements, and that was a bit shocking for me. To be honest, I still can't digest the fact that this is so common. But yeah, it does happen. So as a package developer, what could be some possible solutions? So one would be ship separate binaries per GPU architecture. Works. Worst solution, bloats the package. User has to take in 5 or 6 GB download 5 or 6 GB of a package and then install only one small binary out of it. Bad experience for the user. It's the fastest, but it's kind of the worst for a user. Or I just hack around with the Debian directory files. This can be done, and I would say if I were to really go for a trade-off, I would say this is the most optimal thing to do. But the problem is that this is so fragile, because when you come up with hacks, the point of hacks is you work on a set of assumptions. And as soon as a new version drops in and the assumption breaks, it breaks. And in case of the packaging ecosystem, when one node breaks, you suddenly have a disjoint graph. And before you know it, the entire effect cascades and snowballs into, say, wow, PyTorch can't run on a ROCm backend now. So it can happen very quickly and you won't even realize. So that's why this is not as preferable. The other thing would be that I maybe tweak the build system, which I tried to do earlier, but as I said, they were not allowing me to do that. So this requires upstream cooperation to a certain extent, or maybe you just write a patch. But of course, patches are not preferred, and to write a patch for the build system is a big no-no, or the worst case scenario. I shouldn't even write this here. You just fork that repo and then you just maintain it on your own. You do your own stuff. Of course, almost no package developer is going to do it. It's like literally the antithesis of a package developer. And the final thing is, you go all the way up. You modify the source to support fat binaries, or add generic parameters. This is the most powerful, the best I would say, but also the most invasive method. Because understand this, I am coming from a Debian or say Ubuntu side of things. There are Fedora people, there are Arch Linux people. If everyone goes clamoring around after the maintainers that, hey, I want to ship your source code, so please make this change for me, it just makes their life hell. And it's just not good. So that's why this is the most invasive way. So you need to be this has to be the very last ditch effort that you go for. I have also tried to go for this method, and fortunately the package I am trying to enable Rockham in, those people were very willing. We had to go for a long back and forth, but eventually we came on a common ground, and hopefully we'll soon have Rockham enabled in there. But the point that I'm trying to make is, GPU, so when I ran through this entire process, when I ran you through this entire process, the point I'm trying to make is that packaging GPU software is no longer just a build problem. I mean, I can solve it using this method, that method, but it's a build problem. It is a build problem, but it is not only a build problem. Because even for the hacks that I come up with, I may change a library and add some generic builds to it, and all of a sudden you have, like earlier it was libxyz.a, and now all of a sudden it has libxyz.arch.a. The thing is, this is not a standard thing or something. Every package developer will come up with their own hack, and now the package developer who is trying to build on top of the existing package has to go to the place, and that person has to see that what are the quirks that this person introduced. If someone removes a quirk, again, the entire chain breaks. So it's a policy problem. Portability, you all know very well, it's a very big portability issue. And again, a priority problem. Do I want to ship my code very fast? Then I'll just go for multiple binaries. Like, to hell with the user, I just want to get this done. And that's why I'll just keep shipping faster, but it leads to some trade-offs. The other thing would be that, okay, maybe I will think of my users, but I don't want to go upstream, so I'll just come up with a hack or maybe write a patch. And then the best would be that I care about the users, I care about the upstream folks as well, and I care about the tech debt that hacks will result in. And so I will not do that. And I will simply talk with the upstream folks, reach a common ground, and finally do it. So the point is, it's all about prioritization. And you just don't know what to prioritize, when to prioritize. Maybe, say, in 1 month or so, like it happened with Trixie. When Trixie was supposed to be freezed, the last 1 month is so hellish for all of the package maintainers, because after a while it will be freeze and you won't be able to push anything into the stable branch. You don't want that. So maybe at times like these, I would prefer if I just ship faster, and even if it is unoptimal. But the point is, no one knows what is the correct thing to do here, because maybe there is no correct thing that is defined yet. So the points to ponder is, GPU-enabled Debian packages are still in their early days. Before this, we had OpenCL, but again, OpenCL's main point was to not be vendor-specific. But AMD Rockham, by definition, is vendor-specific. So this is a time where, for the first time, we are facing problems like these. There are times where, I just say that, oh, this is happening, what should we do? And the other folks in the meeting will just go, we don't know what to do about this. So we are all figuring this out. But the point is, why this is important to discuss right now is, what we will do right now will shape how we handle new architectures in the future. Essentially, how packages should react to new architectures. Maybe we come up with some template of how to deal with stuff, and the decisions we will like from the Debian side of things. The decision that we make in Debian may influence other distros, or even vice versa can happen. And more importantly, if we set a precedent for what a clean, portable GPU package should look like in this multi-architectural world, which is going to stay for quite a while, it just helps. The tech debt will be less. We already have a lot of tech debt, but maybe thinking about this right now will lead to a small decrease in the tech debt that we'll eventually encounter. So, questions are downstream workarounds for the technical debt. Should Debian allow multi-arch blobs or enforce cleaner solutions? When should we push upstream? Should Debian define a standard GPU packaging model or something? These are a lot of questions that have absolutely no answer to yet. People should discuss this. We should discuss this, and that's why I gave this entire talk. And hopefully Debian or someone, anyone shows how it's done. And I'll just take one additional minute to just say that just put aside the entire packaging thing for a while. When you think about it, CPU has been so standardized that we take all of this for granted, but the GPU is a hellscape. Everything is changing so fast. There are new architectures everywhere, left, right, and center. And when you think about it, this is not sustainable because we will just have to keep going back to the n-1th version, and we'll have to change stuff for that just to keep things barely running, let alone about optimization. GPU is a very new piece of hardware. This is akin to the era that the CPU folks had when AMD and Intel were trying to get the upper hand of things, which eventually led to the x86 architecture. Why this is interesting to look into is because we have this new piece of new way of compute for the first time after so many years, and the dust hasn't settled yet. So just to be in this space, I'm not saying only as a package developer, maybe even as a person who codes for GPUs. It is just exciting time to be in. Maybe we get to set up a good big precedent. Maybe we become a part of something huge, or maybe become a small part of something huge. But I guess it's very exciting to be in this, and I hope I was able to contaminate your mind with some of my excitement, and this leads to maybe more package developers, maybe more packagers, maybe for Debian, maybe for everyone. People think think more about how to standardize this whole GPU thing, and yeah, that's about it. So, thank you. That's me. I'm Spaarsh Thakkar. Yeah, these are my social media. If you have any questions, you can send an email. I would prefer an email for technical questions, but yeah.
Okay, so one quick question I have from my end. So I work at AMD, though not in the ROCm team. What could ROCm do, or in general, what could any developer do to make a package's life easier? Like, what changes would you do to software to make it?
To be honest, I had a 4 to 5 hour discussion yesterday night with one of my friends, and we thought at several times that, okay, maybe this is a solution, but that is not the solution. I would say one immediate thing that would be preferable is to, maybe we make it a norm that we don't want to optimize everything. Maybe we prioritize one small thing that maybe at least for the sake of it, we push more generic builds, we allow for more generic builds, because at the very least, only the cutting edge GPU hardware will get optimized kernel parameters for them. But for a normal GPU user who has a 3-year-old GPU that no one even cares about anymore, it would be good if some library at least supports them with a ROCm backend. So I think the very immediate step, I don't know if this is the best one or not, is to allow more generic builds, and at least right now with generic builds that use ROCm backend. So yeah, that is one of the things. And overall, a very long research statement would be to how do we make these generic builds more optimal, because let's be real, there is a lot of CO2 emission happening, a lot of energy is being used, a lot of funds are being just burned inside in GPUs. So of course we want to make this efficient, and we need to find some middle ground somehow. Even I don't know how this works, but yeah, that's about it.
One more question. Great talk, by the way, but I'm confused about your comparison with CPU, because CPU also has multiple architectures: ARM, ARM64, x86, RISC-V, PowerPC. So
True.
packaging there also is the same problem here. So I could not understand how.
Yeah, I guess that makes sense. Maybe I gravitated towards comparing this with CPUs, because in CPUs what I see is that there are multiple vendors, but I never have to be like, I am using an Intel Intel CPU, I have to write separately for it, and for an AMD processor I have to write separate stuff for it. I was going through some discussions on this even last night, and one of the folks was like, actually the instruction set is being changed even for CPUs, but it's just that in case of CPUs we have came up with a front end, and the front end is stable, so we don't care what's happening at the back end side of things. As long as the front end is stable, we all can live our lives peacefully. So I guess that is why I gravitated towards CPUs, and my mind was fixated on x86. But yeah, that's a valid thing. Maybe I should take a look at how we are handling for these different things. But one thing that I would go for, even right now when people talk about different CPU architectures, x86 ecosystem is very isolated from the ARM ecosystem. So when I'm anyways packaging, there's a very good chance that there are people who are simply packaging for x86. People are packaging only for ARM. The use cases are very different, but the GPU world is very overlapping. And even if it's not very overlapping, it's just that the vendors are after each other at all times. They keep changing stuff. So on average, big changes are very common. So that's why I get the point, but I would say the CPU architectures live in isolated systems, more isolated than at least the GPU ones.
But the way.
Only one more question. Okay. Next speaker, Kumar Aniruddha, can you please?
Hi. So the question is, when you are getting newer patches into a package, do you and let's say somebody sends in 3 patches and they affect just 2 files, and there are n files and they remain the same. Do you have a system of incrementally building only with the files that get newer patches, or does everything get rebuilt?
To put it very simply, we are using Git essentially.
I see.
And what is not changed is not changed. Patches specifically are only for files that are outside of the Debian directory. So essentially something that the upstream folks wrote about, and
The
now
source
we are
code.
changing it.
I
So yeah, so the point is that you don't want people to pull in the source code. What you want is that you only have a tarball, and that is how the Debian APT stuff works. You get a tarball, you unpack it, now you have the files, now you read the patches, the Git instructions in there, and then you change them to arrive on your version of the patch.
I see.
But the upstream tarball is from the Exactly.
Yeah, and so whatever the rules are, you just sort of run the rules.
Yes.
Build the package. Makes sense. Yeah, makes sense.
Yeah, thank you everyone.